Hello and welcome. This is lecture number 5. Go ahead and get your notes out. Put today's date at the top, put the lecture number. Today's lecture is going to be all about graphs of motion. Okay, so sketch for yourself a displacement versus time graph. Displacement is sometimes called position. We can use both, but it's a XY graph, and something that's important to note is that time is always going to be on the x-axis. For all of the graphs, sometimes this will be displacement position, but we'll also see this with velocity or acceleration. But time is always on the x-axis. And position here is just one dimension of movement. So 1d of movement. We want to try to simplify movement here. We know objects can move in 3 dimensions, but we're just going to focus on those dimensions separately. This might be just left or right movement. It might be just up or down movement. So let's draw a couple different graphs, or you can try to do this on the same graph. But how are we going to interpret different shapes of these graphs? So if we ever see just a horizontal line, that doesn't look super horizontal, but let's say it's flat and horizontal. This is an object that is just standing still. So it's not moving at all. So maybe I've got a tennis ball. I just set the tennis ball down 1.5 meters away from myself, and then I don't move it. I check 2 seconds later, it's still 1.5 meters away. I check another 2 seconds later, it's still 1.5 meters away. It's still 1.5 meters away. So it's never moving, but time is moving forward, so that's why we see this arrow moving to the right, but it's not going up or down because the position away from me stays flat at 1.5 meters. Another way this could look is it could have a positive slope. So we could have a line that looks something like this. So this is moving away. All right, so I set a tennis ball down 0.5 meters away from myself, and I give it a little push. I check 2 seconds later. It's a little bit further away. Check 2 seconds later. Now it's a full meter away. 2 seconds later, now it's like about 1.5 meters away. And so it's a flat line with a positive slope. I think it's right that this has a positive slope. That means that the object is moving away from the observer. All right. Now we could have another positive slope, but much steeper. So how is this different from this example? So let's just say steeper means faster. Steeper means faster. So the steeper the line, the faster it's moving away from you. And one last option here, at least for this slide, is we could have an object that starts far away from us and then starts moving towards us. So this is moving towards the observer. So moving towards. All right, so now what we're going to do if that line is curved. We can have lots of different curves possible, but we might have a curve that looks like this, or a curve that looks like this. These types of curves are getting steeper and steeper. Notice this one I had go into the negatives. Position, displacement can definitely be negative. That just means that there's a positive direction and this object is going to be moved behind the observer. All right, so getting steeper, both of these, means the object is accelerating. We're going to spend many days on acceleration, But just know for now that getting steeper means the object is accelerating. There's another option where it starts steep and gets flatter and flatter. And we can have an example like this or like this. And for that one, we're going to write that getting flatter means slowing down. It's still moving, but with a slower and slower velocity. And we'll learn that slowing down is just a different type of acceleration. So all curved lines are some type of acceleration. Now let's take a look at this displacement versus time graph. Go ahead and do your best to sketch it into your own notes. All right, so what can we tell about this? Let's first kind of tell the story of this object. Maybe it's a tennis ball still. This tennis ball starts right next to the observer and then moves away until it's 25 meters. We can see the unit as meters away, and that takes 50 seconds. At that point, maybe it bounces, maybe somebody kicks it back, it starts moving back towards the observer, then it stops moving for a while, and then starts moving away from the observer again. All right, the slope is the instantaneous speed. So to find slope, we do rise over run. We can pick 2 points. The further apart, the better. Generally, with straight lines, you tend to get the same number either way. But let's find the slope of this by doing rise over run. So rise over run equals how far did we rise? We went from 0 up to 25. How far did we run? We went from 0 to 50. And simplify that, we have an instantaneous speed of 0.5 meters per second. All right, then we turn around. What's the slope on this next section? Well, it goes from 50, 25 down to 60, 15. So a rise over run here, our rise is negative. We went from 25 to 15, so it's negative 10 over our run of 10. So this is negative 1 meters per second. And this is velocity. I know it says speed, but it really is velocity because it's negative, therefore it has a direction. All right, flat sections are going to be 0 meters per second. And then this section here, our rise goes from 15 back to 25. So we rise 10, we run 20. So it's back to having a 0.5 meters per second instantaneous speed. So instantaneous speed is the slope at any one point. Now for average speed, we're just going to connect the very first and the very last dots. So imagine adding in a line. Let's see if I can find a straight line. You add a line from the very first point to the very last point, and then you find the slope of this line, and that's going to be your average speed. So here our rise is 25, our run is 110. So our average speed is 25 divided by 110. Our average speed is 0.227 meters per second. All right, so the average speed is the slope from first point to last point. That really should be average velocity. Let's change both these to velocity. All right, if we were doing average speed, we would want to treat these negative speeds as positive and then average them, do a weighted average for each of their intervals, and let's not worry about that. The average velocity is 0.227 meters per second. All right, how can we find the instantaneous speed of a curved line? Let's say that this is our displacement, this is our time, and this thing is accelerating, so it's got a curve like this. How do you find the instantaneous speed? Well, we need to find the slope of a tangent line. So it's the slope of a tangent line. All right, a tangent line is a straight line that touches a curved line at exactly one point. All right, so now velocity versus time graphs. These ones are a little bit more tricky because time is still on our x-axis, but we're not tracking where the object is relative to an observer. We're tracking its speed at any given time. So it's like we're looking down at the speedometer and we're writing down what it's saying. So velocity versus time graphs can have different shapes, but they mean very different things. Like a flat line, this is a constant velocity. So this object, although it's flat, is moving away from us at a constant velocity. So moving away at constant speed. If we've got a flat line below the x-axis, so imagine that that's flat, this is moving towards at constant speed. And anytime we cross the x-axis, so imagine we might have something like this. Anytime we cross, we have zero speed. So this moment right here represents standing still. And if it's a horizontal line right along the x-axis, then the object is right next to the observer and not moving. Now a positive slope is accelerating. This is acceleration away, and then a negative slope is acceleration towards. That's deceleration. So the positive velocity means it's moving away from you, but it's moving away at a slower and slower speed. So it's decelerating. Like if you throw something in a pool, the water gets in the way and it slows something down underwater to the point where if this line hits our x-axis, it's going to stop moving away. And then it might have the option, depending on what the scenario is, to continue below the x-axis, and that means it's accelerating towards. All right, so a popular exercise is to convert these displacement graphs into velocity graphs. Let's see if we can do that now. So here we've got an object that's moving away from the observer at a constant speed. It looks like that speed is well, let's imagine this is seconds and this is meters, but 1 meter per second. So the velocity here is constant and therefore a flat line at 1 the whole way across. Now we've got an object that moves away very quickly, and it looks like it goes 6 meters per 2 seconds, so it's 3 meters per second away, and then it stops moving. So this then comes back to zero velocity and stays flat right there. All right, so this next one looks like it's got negative velocity. It's moving towards the observer from 6 to 2 meters for the first 2 seconds. So every second it's moving at negative 2 meters per second. Then it starts going at a positive speed away of 1 meter per second. And then it stays flat. So it goes back to 0 meters per second. All right, and these sharp corners are actually not very realistic. Nothing can turn at that sharp of a corner. Everything really should be smoothed out, and these lines should connect, but in this scenario, we've got this object that can just suddenly go from going towards you to going away from you. And so that's why these aren't connected. They're just line segments. All right, next one. We've got something moving away from us. It goes a total of 2 meters in 4 seconds, so it's only a half meter per second. So we need a horizontal line at only a half here for the first 4 seconds. And then it goes towards us at 3 meters per second, so -3 is our velocity, and then it stops moving and goes at 0 meters per second. So that one was 0.5 right there. Now another tricky thing to do would be to go the other direction, start with a velocity graph and draw the displacement. Something is we need a starting position because velocity doesn't tell us anything about where something starts. So these all have a starting position. Now this has a velocity of -1, so that just tells us the slope of this line. So the slope stays at -1 because it's a horizontal line at -1, so the slope is never changing. Now here, we start with a velocity of 0, so that means we're not moving. But then we have a velocity of 3, so we need to now have a slope of 3. So up 3 over 1, up 3 over 1, and then we go back to having no velocity, so another flat line there. All right, this one starts with a positive slope of 2, so the velocity is 2, so we're going up 2 over 1, up 2 over 1, up 2 over 1. Then it has a slope of 0, so we stay flat for a second. Then it has a slope of -2, so we go with a slope of -2, we're moving like that, and then we hit the edge of our graph. And for our last one, slope of -1, it's going to look like this, up to our transition, where we then have a slope of +4 for just a second, so that means 1, 2, 3, 4. Real steep line there, and then we have a slope of a velocity of 0, so a flat line there. All right. Now let's take a look at a couple that are curved and see if we can go from displacement to velocity. So we're not moving, so velocity is 0. But then we start to accelerate. So now we're going to see a slanted line on our velocity graph. And so it's going to slant. It looks like it's accelerating. Eventually, it gets to a slope of 2. So we're going to diagonal line up to 2. And then it stays steady at that new velocity. So for the first time, we see a diagonal line corresponding to this curved line here. So curved equals diagonal. Everything else has been flat so far. All right, now this one has a slope of 1, so we'll just have a flat line at 1. And then by this point here, the velocity hits 0. So I'll just mark that point there, and then by here, the slope's back to -1, and then stays steady at that. So this is going to be a diagonal line going from a positive velocity to a negative velocity. All right, now we got a slope of 3, so a velocity of 3, but then the velocity starts to level out to 0, and by 4 it's at 0, so this can be a diagonal line down to 0, and then we stay at 6, so our velocity is 0. And here we've got a velocity of -2. At 3 it hits 0. And then by 4, we're back to a velocity of +2. And we'll connect that up as it slows down and then starts to accelerate away. So that's that for this video. I'll embed a few more questions here. Answer those. Make sure you let the video play out. Have a great rest of your day.